Another draft science video. Yay. This one, two slit thing. Getting closer, I think. Getting close to the nail in the coffin. Yeah, the nail in the two slit bullshit coffin video. Anyway, alright, so this was interesting. It's just a single slit. You know, the front and Frauenhofer, whatever. Whatever. Then you have the other guy, Fritten and Frotten, or whatever the fuck it is. Fritzen. Anyway, the inside, outside. Anyway. Alright, so it's just a single slit, variable. And so I'll just play a little bit of this. I don't know if we need the sound. It might just get in the way, so I'll get rid of that. And the thing to notice is right here where the little fringes change. So there's three there showing. And as you watch them, oop, pops right in. Kind of pops in. Kind of pops in. Pops, pop, 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 pop. And you can sort of see the adjustment. The rest of them adjust. And there does seem to be a lag. You know, a little bit of time. It takes a little bit of time for the pressure to go from, hey, there's a new one here. So you can see them stretching in. They're stretching almost in an elastic way. And, boy, that's something to work on in terms of proving that one. You know, in terms of, well, here we went the other way, so it went a little too fast, but let's just watch that. So now they'll be popping out when he goes the other way. So now he's almost all the way. Now they start turning it open again soon. So they'll be popping out, and so you get the idea of him getting wider. So let's see if that's like they'll just see he's going too fast. Yeah, so you can't really get any idea of it. But anyway, I think that's an interesting. If I'm right, then what that's illustrating is the electrons popping in to the empty space. Extra electron, extra electron, extra electron. And the compression evening out across the electrons. So, you know, point from my side. Maybe not a big point, but like I said, if somebody does this experiment slower, very slowly, and can film it better, you know, I got yeah, like I said, I got a laser, a green one anyway, waiting for glasses actually, because yeah, I realized I really can't afford to go blind, and they'll sell idiots this shit, you know, real idiots like me. There's a lot of dangerous stuff you can buy now, which is, you know, it's nice, it's fun, but shit, you know, I guess, well, they sell guns to idiots, so what's news? Alright, anyway, so let's see, should we go back to this two slit math thing, just to verify certain points. So again, I just want to point out that let's just get to where she has both drawings on top of each other. There we go. Alright, so this math, so Pierre was bitching about math, so we'll do some math crap. You know, it's just a simple equation. I mean, you're just talking about distance, this D, and this L. So the L is the distance from the target. The D is actually the distance of the impediment in the double slit. Alright, then you have the wavelength, and then these arbitrary M numbers are just numbers for the maxima. And in the single slit, it's the numbers, the M's are for the minima, which is, you know, weird that the math is inconsistent that way. And the D number is for the width of the opening. So in this one, the width of the opening is assumed. You're not allowed to change the width of the opening. There's no place in the equation to put a different width in. It's not provided in the math, which kind of anyway. Okay, so let's go to the Puro version, you know, there's so many ways they can do this math. Well, not so many. Okay, there's a few ways you can see it done. You know, with starting assumptions and you know, what am I looking for? What word am I looking for? Something about back in Frauenhofer. So this is like the standard kind of way it's done, and And so this is the Huygens idea, where you just create a tiny bunch of, they even use the word infinite in here. Assumption of infinite source distance. Source distance. So I guess maybe that means the source of the light. But they really do an infinite number of little wavelets. But the standard way is really all you're talking about is the length of these two lines. So what you're really saying is let's just take the wavelength. They usually go from the middle here to here, and they use that arc. And they say, well, that represents a wavelength, and it's what percentage this line ends up being of a wavelength is essentially the equation. That's what the sine theta is doing, is it's taking a percentage. What percentage is the hypotenuse of these two lines? Like, what's their proportion? And this extra is the piece that will be left over. You get a more refined number, and then you could just place that number on here, and you could just say, well, is it half a wavelength, or is it 3/4 of a wavelength? And that'll tell you whether if it's a half a wavelength, then it'll be a minima. If it's a full wavelength, then it'll be a maxima. And that's all you're getting. So it's just, there's nothing. The math is rudimentary and kind of simplistic, in some respects. It's the premises establishing the math that's the argument. So Piro really doesn't understand that. I mean, I'm perfectly comfortable with the idea that there's a relationship between the pattern, this distance, well, here D is this distance, which is kind of funny. They're using A for the aperture. But anyway, the aperture size, the wavelength of the light, and the distance from the target. Yes, those are all variables that are important. No one's arguing that. The argument is about the rest of the convoluted gibberish. So I'll go back a couple of things here. I think, this is where you really get the idea of the convoluted. So here's another way to do the intensities. So they're doing, before they were establishing where the maximas were, and then this is the intensity math, which gets really convoluted. And it's really, they're just cheating, because they're just turning a straight line into a curve, and then using the curve like a sine wave or anything else to just create a gradation. So, I mean, obviously it's the thickest here, and it's going to be the thinnest piece of pie over here. So you could just almost draw these lines and say these are going to be relative to the proportion, almost invert them, actually. But you can establish any kind of ratio. Once you establish the curve, you can make the curve into, you can do the convex of the curve, you can do lots of things with it to make a proportion that'll end up establishing a ratio. Like for every inch here, you got 3 inches here, and you divide by pi, and that'll give you a ratio. So it ends up being this 25:1 kind of thing, which I think is a little bit, I mean, I've never seen a pattern actually that in my opinion reflects what this math says. Because some of this math is basically implying that in a multi-humped pattern, that this ratio would be 90% still, and it really isn't. So I don't know how they come up with that crap, because it doesn't fit for different size slit openings, that's for sure. So anyway, I just wanted to play with this idea, though. I just said, oh, yeah, I can do that too. So that's sort of like the Huygens idea. The whole Huygens principle is that you want to turn a flat wave, and especially for Piro's purposes, in terms of wanting to create his diffraction and such. They want to just turn a flat wave into a round wave. So they're saying light is like water. We know that for water waves, this is friction that causes this. Okay, the barrier creates friction, tension, and it snaps the tension of the wave and releases it from the water here. And so that's why it goes out and it spreads, is because it's been released from its tension by the impediment. And to think that light has that property is to imply that a single photon somehow does this stretchy thing in a wave-like manner. And it just, to me, I mean, it just stretches credulity to say the tiny photon goes across the entire slit stretches, breaks, and then creates rounded waves. You know, it's just a silly argument, in my opinion. But I mean, once you do this, once you create this round thing, then it's very easy for you to understand how these distances are different, and you know, you're going to get this different. You can almost create your own little facets, because you can say, I can pick any point and just put a little straight line there. So I can just do this Huygens game again. I can make a round line, and then where I want to, I can make it flat again, and just say everything in that area goes straight. Everything in this area goes straight. Everything in this area goes straight. And then I automatically have created my minimas, you know, my maximas and the minimas. And so anyway, you know, it's fine. I'm just saying there's lots of algebra, you know, geometry you can apply to this, and that's what they're doing here basically, as explanation. That's fine. I mean, I'm not against that, but I'm just saying, I'm arguing that the notion of what's happening, giving photons these incredible properties, is the part that I think is crazy. So my alternative now, as I would think of it, is, alright, so we got the idea of this pressure idea, that electrons are under pressure. So I've mentioned the Venn diagram a few times now, but the idea is this pole sits there with a little ball at the end, and you shoot up a bunch of electrons, or you pull out of a bunch of electrons, and what you do is you create a potential that goes through this entire field of atmosphere and electrons. And it can go for, you know, in the case of what's his name, the guy I don't like too much, you know, the guy who hated Edison, you know, thought he owed him $1 million. Anyway, that guy, Tesla. You know, Tesla is, you know, has famous pictures of him sitting in his chair with giant lightning bolts flying around his head and stuff. But that's all, the electrons set that up, and, you know, setting up their potential. So I've made the argument that the protons have more gravity to give, so to speak, more attraction, more low pressure to give than just the electrons they're holding in their orbits. They spread some more out. That's just not strong enough to hold an electron, but it's strong enough to give one a comfortable place to sit. Just like our solar system is, you know, has gravity outside of it that nothing's in. It's still there, and anything can, you know, sit in it for a little bit, drift in it, you know, and if it was moving very slowly, it could probably sit in it for quite a long time. Anyway, comfortably. So the point I've made is that I think what's happening is that electrons fill these gaps, and that you know, they are the things being interacted with. And so I thought about this drawing, and I was saying to myself, well, yeah, and the electrons would fill the gap based on the same kind of idea of the gradient, the same idea that the Venn diagram creates a voltage difference. So at this far out, it might be 2,000 volts. At this far out, it might be 5. At this far out, it might be 10. At this far out, it might be 100,000. So depending on how far away you go, the voltage gets lower. So it's dissipating by the R squared, the same rule as gravity, by the way, people. I mean, all these things are not coincidences. I'm just saying, you know, the fact that all the forces move the speed of force, light, is not a coincidence. The fact that the R squared rule comes out all over the place in a lot of Maxwell's equations, and even the idea of the R idea, because of the way conductors work, you know, because they're infinite in one direction and finite in the other direction, so it's only an R value. I mean, it's all connected, you know. Obviously, there's one force, just different manifestations of it. Well, anyway, so the electrons are lined up, and what they're going to do is they're probably going to line up in what's going to end up being that same kind of proportionality. The further away you get, the weaker the force gets, the weaker the connection, and they're going to do the same basic thing in inverse of the magnet or anything else. They're going to create they're going to create a field line, so to speak, a charge line, whatever you want to call it, electron charge lines. They're going to be different than the magnetic charge kind of lines, but it's going to do the same thing. They're going to spread in this not linear manner, and this gives you even more reason to suspect that, you know, it's happening on both sides, obviously. So when light goes in, I might argue, okay, that if light hits at an angle, it doesn't do anything. It can only transmit the force if it hits perpendicular. So the only light that hits straight goes straight through, because it's all straight reflection. I mean, it's all straight vibrations. But if it hits off angle of it coming in, it doesn't mean anything. And the ones it's really hitting first are these ones here, these electrons. And then these electrons are passing the force on to each other, and as they pass the force on, it ends up being deflected in an angular direction. And so each angle is a little different, and you get the interference pattern. Yay! So I'm just saying, here's another simple mechanical description that doesn't require any Huygensings, and you know, we don't need to do Heisenberg anymore. Where the photon will end up will depend on where it hits inside the slit. If it goes, like I said, down the middle, it's definitely going through. Some of them will get through because it'll just miss everything. It won't hit one of these ones in the middle. So most of the light ending up right there at the center, because this slit is very small by comparison to the size of the target. You always have to remember that. So anything that ends up going right to the middle, which is consistent with the outcome, which is a much stronger maxima in the center. And everything else is kind of dependent on this arrangement of these electrons. And the force, technically, it could go both ways, depending on which trail of the divergence in the field, the spreading of it, you know, this effect. So it's this just modified to this equation, and I think this is a perfectly suitable, just as good as explanation. And the point would be to just quantize it, you know, get it down to an exact statement about the number of electrons and the nuance, if you want to say. So there'd be a lot more. So the point another point I was making is there'd be a lot more electrons on this outside ring than there is between the two slits, and so that would give you a finer granularity to the effect also. So it would be less visible in terms of, what's the word I want to make? Spreads it out a little. No, it's not the word. Blurs it. I don't know. Probably not the right word either. But anyway, so I'm going to work on that with just the aperture argument first, because I was thinking, see, this field thing works in 3 dimensions really well. So like a dome around an aperture, if you can see what I'm drawing there. So it would also explain the Newton's rings really well, and I think it will explain so I really want to try the triangular aperture. People don't play with that much, but it creates very interesting patterns. On each side has a different kind of pattern, and you know, it's you know, so I mean, it would be interesting to try to figure out what, you know, through maybe some Maxwellian equations, what exactly the shape of this dome would be, you know, on a triangular aperture. How exactly how the field lines would shape. I would imagine it would try to do something like that, to try to do the rounding thing, and then it would round inside the triangle. I'll have to figure that out.
Could be.
So anyway, I think we're cutting it down. we're getting to it, And I mean, I think I've pointed out some pretty glaring flaws in the mathematics, in the sense that the double slit math, let's see if I can bring that up, you know, it has this glaring deficit. Single peak, you know, that's no single slit. Yeah, you just can't trust hitting one of these things. Just gets me into trouble. Every time you hit one of these, you get a shittier diagram. And this is written so badly, I can't even tell what these squiggles are, some of them. It really didn't do a very, you know, it's not, it doesn't center on the page, which is really irritating too. So it's single slit still, single, yeah. So I think that's where we got.
Could be a new post.
Here. No. So anyway, I won't waste too much time on it. But you know, the point is look, the double slit diffraction math, traditionally done, it's kind of insane that in the equation, the width of the slits is not relevant. They just care about this width, or the impediment, and they just assume this width. And you know, that's kind of bogus. I don't know why it has that glaring missing bit. Like, what if you vary the size of the slits, which seems like a rational thing to do, and vary the size of the middle? How come the math doesn't have what the math can't answer that question? That's kind of the statement being made is, no, we don't have math for that. Seems a glaring omission. But anyway, yeah, I think that's you know, I just cut it short just because I'm just saying this is my new thought process, though this makes a lot of sense. The electrons would all rush in. I mean, they're all going to, they're not going to rush in for any other reason than the external pressure. The external charge is greater than the internal charge because these are nice available protons. They're all going to feel the need to get in there. The first ones in will establish their ownership of the space. As you tighten the space, you will readjust these, all these field lines will be readjusted as these electrons slot in and out. And like I said, there's some indication that that's exactly what does happen when you slowly increase and decrease the slit size, is that you're basically watching electrons pop in and push their neighbors. And I think you can see some of that actually. So that will be the video to find, is somebody who moves the slit very, very slowly, and they open the aperture in the camera to really focus on the trailing of fringes. Alright, probably enough of a video. Keep it short and to the point. I think I did that. Probably missing something. There's probably something else I wanted to show, but it'll wait till next time, I'm sure.